background.
Okay, okay. Nice background. Okay. I thought that you were in a plant and you would show us some live processes.
Well, I did have intent to show you the live process because the video doesn't play on Zoom.
Okay.
Uh,
Yeah.
what I've done is I've uploaded it on the website india-inspires.com, and I'll send you the link to it also, so you can play the video from there and download it and whatever. So the video is available.
Okay. Thank you very much.
Vijay, can you make Mr. Marwa as a panelist and also Asha Nangia ma'am?
Dr. Agarwal, Mr. Marwa has already joined. So should we start?
Let us start.
Also,
Mr. Marwa sir, if you can just give the welcome remarks.
So, good afternoon, everyone. Welcome to this second tutorial in the series on semiconductor fab and ATMP. So, we are very grateful to Dr. Ashwini Agarwal, who has taken up this task, and as already pointed out, the last lecture on last Friday, it was extremely informative, where he explained us the fab technology, the physics behind it, and then the types of fabs and what all goes into a fab. So that was all very informative. And then, the concept of the integrated device manufacturers, fabless companies, so all of that. So I think everybody would now be on the same page, and we did learn a lot from the last lecture. And today he will be covering the ATMP part of it, the assembly, test, marking, and packaging. And that is also called OSAT in the industry terms, outsource assembly and test. So here we have different specialized companies. For example, in the fab, we had the IDMs, integrated device manufacturers. We have Intel, we have companies like Samsung. And in the foundry side, which do the chip manufacturing for the fabless companies. So we have, the biggest is the TSMC in Taiwan, UMC, and Global Foundries. So those are the companies which come under the foundry category. And today he will be explaining us the ATMP part of it, the backend of the fab, and which again has specialized companies such as ASC Technology, Amcor Technology, etc. So over to you, Dr. Agarwal. Keenly looking forward to your tutorial. Thank you.
Thank you, Marwa sir. It is my pleasure to take the team through the session today, which will primarily focus on assembly, test, marking, and packaging of semiconductors. So that is the title of the primer. You know, we covered in the last round these basics of semiconductors with manufacturing device types and a very brief overview of industry. And we said that in future we'll cover the evolving frontiers, which are the ATMP, wideband gap semiconductors, and India options. So this is the plan for today. I will be covering the semiconductor industry briefly, filling the gaps of the last discussion, and taking a step into the ATMP. And by and large, today's session will focus on ATMP, which is a session and a subject in itself. And I will briefly cover wideband gap semiconductors, preview of it. So that also is a subject in itself, but I will have 4 or 5 slides to just lay the basic concept before we close the session. So that is how I have planned this session today. So if I go on to this without further ado, here skipping the intervening 90 slides, and we are on to semiconductor industry. And this is one slide fill up of the last session. And that is, the industry, as you can see, has been growing year on year for the last 2 decades. In fact, ever since its inception. And its growth is being driven now by factors which are beyond computers. It's actually going into so many other industries. It's become a meta industry. It goes into communication. It's going into consumer, automotive, industrial, and it goes beyond. It will go into pharma. It is going into AR, VR, and the categories that it is going through are really exploding out exponentially. So if you actually take a look at it, The industry is valued at about, its peak was 468, $469 million in 2018, and it dipped a little last year. Uh, uh, it's expected to be at around $426 billion this year, 2020, despite COVID, and it is expected that it will actually leap beyond 450 billion next year. So it is again it's an industry with a tremendous growth potential in it. As such, its supply chain is also tremendously fragmented. It is tremendously detailed. You've seen this last time from semiconductor foundries and ATMP companies that the
Sorry to interrupt you, sir. Your screen is not, your presentation is not visible.
It is not visible. Just hold on.
Yeah.
Then let me get back into this. Why would it not be visible? Is it coming on now?
Yes, it is. It is.
It is
No,
coming on. So I'm putting a screen.
Presentation mode, yeah.
Yeah. So basically what I'm sharing here, let me go back to the previous slide. The drivers of this particular industry, almost, it's rising to about $450 billion next year, despite COVID impact this year. It's expected to be around $460 billion next year. Communication is a key driver, but then it is growing into all other sectors that we are talking of. There are some which are mentioned here, but it's going beyond that into medical sciences, healthcare, packaging, and a lot of other sectors which were not, conducive to electronics way back. If you take a look at its supply chain, it's also very, very comprehensively developed. At the top extreme end and the upstream is the foundry and the ATMP organizations. Then you have the vendors, the distributors, that take the devices to the manufacturing companies, which is EMS companies. From there on to the OEMs, and finally the equipment is getting distributed out to the end customer. But actually the supply chain is much, much more complex than the previous slide that I showed. And it is getting fragmented and it's getting fermented year on year. So if you actually take this version of it, which was holding for the last 2-3 decades, you'll find that the original IDMs fragmented first into IDMs and foundries, and the foundries evolution was a result of fabless companies also coming into play, which actually focused on design and creating a unique IP out there for specific markets. And then, this has been growing because beyond the design houses, there are vendors and outsourced design houses who take the job from the fabless companies and create the designs for the foundries. So this was the structure as it was before. But in this session, as we go deeper into what is happening with the industry now, you'll find that it's actually fermenting it in a very classic, brutal manner, with different players coming into different zones which they were not originally playing in. Fab itself has a potential to create a huge opportunity in our ecosystem. The equipment and infra is one part of it. The materials is the second part of it. The utility is the third part of it. And if you actually take a look at the role that it will play in the entire ecosystem, it's crazy, because it can actually be the center point which will pull in a lot of other related ecosystem players. So it's a pretty complex engine, getting more complex as time goes by, and we need to actually get a handle on it. One of the things that we always felt was that India has a huge strength in the semiconductor design, which is a fact. It is a strong base for the MNC global engineering base, and only thing is its own design base. Startups are really very weak, and they may not be as up to date with the latest EDAs as expected, which is an exposure to the country. At least some steps have been taken in the country to build this fabless design base, and I'm sure that the results will be visible as time goes by. The OSAT landscape, this is the global landscape here, one version. a couple of years old slide, but it shows you the key players. And you have ASC leading the pack. And ASC has also been growing, by way of inorganic growth tactics like acquisitions. So AC is really the leading OSAT company. TSMC is the leading, AC is an OSAT company. So it's an outsourced company, while ATMP company, while Intel and TSMC are the leading ATMP companies. Again, we'll discuss this in appropriate data a little down the line. But this is a very big industry, the OSAT. It is valued close to about $28-29 billion right now, and is expected to become $40-50 billion in the next 5 years. This is actually a very specialized industry because they are not doing the conventional wire bond. They have actually moved beyond it, and we'll understand what is the latest advanced packaging that is being talked of. What is that advanced packaging, and how do these people play in it, and what are the technology trends and possible manufacturing directions in that particular area. So if you actually take a look at it, it's not that OSAT opportunity is small. We believe that the latent potential for this is around $600 million. And there are two different methods by which we estimated this. And we looked at what could be a segment strategy that could drive it. We feel even if we take a point segment strategy, it should be an opportunity to capture at least about $80 million of OSAT opportunity here. And these figures are something we can discuss separately. SCL is an amazing, proof point that we have. I don't know if you're seeing my screen, but I have in my hand a lovely book from my library. I really treasure it. It's called Captivating Views of India, given to me by Dr. Kiran Kumar. It shows the photographs of India from the space using our CMOS image sensors in our space program. And that is perhaps the biggest pride that one has in SCL Chandigarh. It is a proof point of India's capability. When applied material engineers came to India and they first interacted with SCL a few years back, they were zapped at what they were seeing. They said, we never believed that this existed in India and that you had these sort of capabilities in it. And believe me, we have nothing to be shy of the 180 nanometer or 600 nanometer production lines at SCL, because they are producing radiation hardened chips, which are actually functionally created at higher feature sizes than the commercial chips there. So if you take a look at it, the key message in this part is very simple. Semiconductor manufacturing is a critical element of the national electronic policy. It is pervading, it's actually going to go across all the industry segments for the next few years. And there's going to be huge opportunities in supply chain, logistics, materials, and supporting areas if we tap it properly. So now let us go back to the evolving frontiers and the evolving frontiers of semiconductor packaging. Again, I'm not sure. Can you see me? If you would, I have a fruity package in my hand. And we're starting a session on packaging. So my first question is, what do you think is the role of a package? Conventionally, we'll say, if I have a fruity package in my hand, it's there to protect what is inside that package. And that's not wrong. It is to protect that juice. It's got to preserve its functionality, enhance its functionality. And that's what is the function of the device packaging part of semiconductor manufacturing. That's what it has to do. If you actually take a look at it, packaging is really fundamental to our way of life. And ATMP, you are doing what I talked of, the conventional packaging. It protects the semiconductor device in the package. It will enhance, it will preserve its functionality. It could enhance its functionality. And we will take examples of it where, functionality is enhanced the way it is packaged to get you a better, for example, better imaging. Okay. So there's the new iPhones, they have a front side image and a back side image concept. And that is primarily a packaging related innovation to get you less scattering of light inside the package to get a better and sharper image out of it. And really, since we are talking of iPhones and Mac, this visual is actually profound. It shows you how the entire electronics is also evolved, how mankind has evolved. It has evolved. So if you take a look at the phones, the sort of phones we handled maybe 15 years back, if you remember, they were so big, even hand phones, they were so big. And now you have an iPhone which slips into your pocket. What is happening on this? How is the electronics all shrinking to come into that particular small package? And really speaking, the packages have been evolving. Semiconductors have been evolving. So this is something most of us who have done electronics will be familiar with. The ICs of the 70s that I played with as a hobbyist and in my masters in electronics, but this bug-like creature is the father of packaging, the dual inline packages. And as you can see, the device is put up in a molded package, and there are connections made to these pins or legs that are there. And because of the nature of the package, how much can you really expand on it? Because as you want to take more and more logic into that device, into that die, you want to have more and more interconnects out to the real world. And therefore, how much legs can you deliver on this sort of a package? So dual inline package actually had to evolve, and it evolved to what was called the QFP. And you may remember these sort of CPUs and processors on the original Tandy TRS-80, and this was a quad flat package. So dual inline package or DIP package gave way to QFPs, which were capable of supporting up to 200 IOs. And then in mid-80s came the PGA. And you possibly saw it when you looked at a Pentium motherboard. And this is a pin grid array. And it would go and the pins would fit into the socket on a motherboard so that it could be replaced when required. And typically a PGA processor would have a heatsink on the top of it. And that's how the motherboards were configured in that era. And if you actually take a look at what has evolved in 90s, is this thing called a ball grid array. And let me try and share what this is. This is something interesting. If you take a look at it, where is the die in a ball grid array chip? This area where there are no ball grids is where the die is. And why is it that there are no connections, no ball grids laid in under this die? That you can get a feel from this image that I've got here, where in the schematic you can see there is a die, and then there are connections being made from the active surface or die. The active surface or die is on the top. And from there, you are actually taking these wire bond connections onto the carrier. So basically, the ball grid array is a carrier board on which there is a die, on which there is a molding compound or epoxy to actually seal the die. And in the die, what you're doing in this package, what you're doing is you're taking these gold wires off from the active surface and bonding it to the carrier substrate, which has vias or connection interconnects, which are leading to these solder balls or pins under the carrier. And it is from those that the connections are made to the printed circuit board. So this also is something interesting because this is where transition has taken place on the ICs. If you take a look at the earlier ICs, they were all through hole soldering designs. So you would actually have these pins which would actually go through holes, and it would get soldered on those holes. And when you actually come to the ball grid array and subsequent evolutions, what you're actually having is a surface mounted device. Okay. And in fact, most of what you see now are surface mounted devices. And this is how a ball grid array package would actually look. So if I take a typical iPhone motherboard, you'll really see that there is something different about this motherboard. It doesn't have any visible, electronic traces of the motherboard. What we worked with in the hobbyist era of 80s, 70s, there is no copper traces visible on it. Everything has gone into that PCB. And in fact, if you take a closer look to this board, you'll see that there are these ball grids which are actually connecting onto landing pads on the board, which are perhaps going in, and the circuitry is all inside that PCB. Okay, so this is where the ball grid array also started evolving into a new evolution called the flip chip ball grid array. And this is actually the dominant package in the marketplace right now. And if you actually take a look at it, what it is doing is the chip is now flipped over. If you take the previous era, the active area was on the top, but in the flip chip, the active area is brought down next to the carrier substrate, and the active area is directly connected through micro bumping onto the interconnect points, on the carrier substrate. And from those interconnect points, there are subsequent redistribution of the interconnects to the solder balls on the carrier substrate at the other side. So this is a very interesting thing, because with this evolution, a lot changes. With this evolution, you can just imagine if the active surface is facing here, and the you are not having the wire bonds. First of all, you are eliminating an interposer intermediary substrate. You are eliminating the gold wire bonds, so you are going to save costs, and you are going to have a thinner package. Your package is going to be thinner as compared to the wire bond ball grid array. And what you're seeing on this is actually because it is so close, to the top of the surface, and silicon is a good thermal conductor. It has an implication on the thermal conductivity and heat dissipation of the flip chip ball grid array package device. So it will give you a better thermal property as compared to the previous generation ball grid array chip package. So the packaging is evolving from 70s to 20s and beyond. There has been a tremendous shift of the packages, and these are only some of the packages that are being shown on this particular slide. So you have dual inline package, and then you had the quad flat package, and LCC is leadless chip carriers, where you can see there is no lead in it. There are landing zones which define the connection points, the pin grid arrays. This is the wire bonded ball grid array. These are the single online and thin single output devices. The system in package, the flip chip ball grid array, which we just talked of, and the chip scale packaging is something we'll mention a little down the line, wafer level chip scale packaging. And then you have this again, you will see there are no solder bumps in it. It is quad flat with no LEDs. And that again is used in some type of packaging. You have the current evolution and the dominant play in the last 5 years has been of the fan-out wafer level packaging. And here you see also the other versions of it coming, the 3D wafer level packaging, embedded system in package, panel on package, panel, 3D ICs, fan-out panel on package. And these are terms that I'll try and explain over the next few slides, so that you get a feel of how the packaging industry is evolving and why. And the key thought which is there is that there is a tremendous fermentation taking place in this industry. You have major system integrations happening, which is why you're seeing that phone slim down as dramatically as it has for the last decade and a half. You are actually seeing that pressure come up on the device equipment board, from there onto the system packaging. In fact, it is moving to system on a package where multiple dies are coming on the same package, and a lot of functionality is being squeezed into that package. So a lot of what was being done by the EMS on a PCB is slowly coming into a system in package. And then a lot of what the semiconductor die is doing, that capability is also moving up. And this is what is creating the next generation of packages. So you have multiple dies which are there perhaps on a carrier, the package substrate, which is connecting on to the dies via micro bumps, and redistribution of those electric connections is taking place to the solder bumps, which is finally connecting onto the printed circuit board. And this is roughly how the package is construed. But how you reach there, it's a major technology journey, because you have to actually not just make these connections to make sure that they are done right. If there is any oxygen bump left into a solder ball, it can have tremendous technical implications. So there's a lot of finesse to that final device that takes place. This is one view of the packaging family platforms that are there on the in the current world, depending on the substrate. So the most advanced packaging, there is no substrate. The fan out and wafer level chip scale packaging, you actually are cutting out the cost is substrate. And then you have organic substrates, lead frame substrates were there originally. In fact, if you go on to YouTube, you'll see some of the earlier ATMP lines videos, which are going to use wire bonding on lead frame substrates to create the packages. And then you have specialized substrates like ceramic substrates. SCL has ceramic substrate capability out there. And if you want to just look at what is advanced packaging in this, I just knock off the wire bonding. Okay, I just knock off the wire bonding packages, and this is where the advanced packaging is. This is what we call the advanced packages. This is where the world is right now gyrating towards. So if you take a look at the world of ATMP, key message, there is a drive to get more logic into the chip. This is creating a drive to get more IOs for that particular chip, because it has more functionalities. You need to get that functionality, that capability out, and you have a drive towards lowering the cost of those IOs. And this is creating also an evolution from that original single die assembly test mechanical marking and packaging to a wafer level packaging. And wafer level packaging is critical because really you are now processing everything on a wafer, and we will again see a little more of it, how this happens a little down the line. So if you take a look at it, the previous era was where you had very clear defined front end packaging, front end of the line, a front end of the semiconductor manufacturing, and a back end. And you could see the front end processes, or what we discussed in the last presentation, where you are actually creating the active circuits on the front of the silicon substrate. And this involves doing all the oxidation, creating the dielectric layers, depositing different types of materials, planarizing them, passivating them, then selectively patterning on it, etching on it, selectively creating those shallow trench oscillations, creating those vias, creating the the transistors by appropriate doping, and then building the interconnect. And the device itself was actually tested, diced, tested, and assembled on a lead frame separately. That was the back end. Okay, the finished wafer was diced and then assembled on a lead frame in the back end. But in the current era, when you're looking at wafer level packaging, you are actually replicating some of the front end process of creating those interconnects at the die in a mass scale on a wafer itself. Okay, but it can't be the conventional wafer. It is actually a little different. and we will just cover it very shortly. So this is the fundamental difference that is taking place. The wafer level process versus conventional. The conventional, you went through the silicon wafer process, you did the created the wafer, you do a die sort test, mark the die which is bad, okay, dice it, and good dies are taken into an assembly sequence where they are picked and placed on a lead frame. They are subjected to, you do the bonding, you do the function test, you do the packaging, you do a visual inspection, and you take it out, after the function test and visual inspection, you take it out to the market. But if you take a look at wafer level package, after you've created your silicon wafer, the finished wafer is actually, you are doing something different. You are doing a wafer level packaging, and all the good dies are again taken and put on a carrier 300 wafer, for example. And a molding compound is laid on it. On the carrier, you have an adhesive on which these dies are going and sticking, and on this you mold it, and after it is cured, you start processing it to create the redistribution layer with all the interconnects, and from there you are taking out the chip. So we'll take a look at this process a little more in depth, a slide down the line. So first, let me take you through a concepts that are related here. You will hear this term a lot. So you will have fan-in wafer level packaging as of now versus fan-out wafer level packaging. And, we had a couple of years back in 2018, Tisol, a leader had gone on the ISA Visions platform and said that he will create a fan-in chip scale packaging project in India. And for that, if you actually take a look at what is fan-in chip scale packaging. So a chip scale packaging is when the die or the chip and the final package do not differ more than 80%. So the outer package versus the chip itself, its ratio is 1.2. Okay, and if this is a die, all the solder bumps are effectively under the die. Okay, so what does it mean? Actually, it means that all the redistribution layers, all the interconnects from the die are being taken to all this ball grid array under the die only. Okay, there's no ball grid being taken beyond the size of this particular package. So this actually puts a lot of restriction on the size of the solder balls in this particular package. Okay, on the gap between each of the pitch between the solder balls. Okay, it is also going to come under pressure as you go to lower and lower die size, because in semiconductor we are going to lower and lower die sizes now, so it can be tremendously a pressure to create devices with fan-in wafer level packaging now. The fan-out wafer level packaging is therefore the way to go, and that's the direction industry is taking as of now. So let's take a look at what is happening in the fan-out wafer level packaging. You have a die, and the connections are getting, interconnects are being taken to solder balls which are beyond the die area. That's why if you take a look at the die in a fan-out wafer level package chip, you will have ball grids not just outside the die area, but even under the die area. Okay, and there is no restriction for the ball pitch. You define the IO. You can have as much IO as you want, and you are not restricted by the ball pitch. And this is interesting. So the single message here is, in fan out, the redistribution line traces are routed both inwards and outwards as may be required to create a logical, sensible, manageable grid array, solder ball grid array at the output. So it is a very popular device, package device now, and pretty much field proven. And you'll find this very common in the evolving mobile semiconductor packages. So if you take a look at the wafer level packaging, this slide, the only key messages, you have two movements. One is the fan out wafer level package, which is one move. The second is an embedded, design, embedded die in a PCB, which is what you're seeing here. So as you can see here, you have multiple dies, and you will have multiple dies coming up in this also. But this is more PCB laminate based. This is more on the wafer integration base. So we can discuss that again a little down the line. But this is the size of the market. Just about a couple of years back, when somebody had asked me, it was very simple. The size of the ATMP market was $50 billion. Roughly, the size of the advanced packaging was around $25.5 billion, and the size of the the easier or the wire bond and the basic packaging was around $24.5 billion. Today, it is just the size of the advanced packaging is around $28.8 billion, and it is growing, and it will cross $40 billion, somewhere between $40 to $50 billion is what it is likely to be by 2025. And you're seeing the growth sizes here. The wire bond market, the basic packaging market, is almost stagnant, growing barely 2 to 3% a year. If you take a look at the advanced packaging market, it is overall growing at about 7-8%, as shown on this particular slide. And the growth is primarily in the fan out. It is in embedded die 3D stacking, or the multi-chip device creation. And it's actually, this is the area which is growing at a breakthrough pace. The 3D stacking, ED, and fan out. So it's getting actually driven also by the overall industry technology roadmaps, as companies are packaging more and more at a smaller and smaller resolution size, and they are trying to push the Moore's law. The Moore's law is in turn getting driven not just by CMOS scaling, but also by advanced packaging innovations. And in fact, advanced packaging is pretty exciting, because it can not just change the not just give the interconnect between the lower size die and its functionalities with the real world by giving those connections between the die and the PCB, but it can also enhance some of the functionalities. And in fact, I've got complete presentations on how it can be customizing. Packages can be customized for communications, for power electronics, for medical electronics, and so on and so forth. So very, very exciting. And if you take a look at it, the market's actually, very dominantly, led. These are the players. The dominant players are TSMC, which is a foundry, and TSMC is actually taken over SPIL. So their market size is actually around 22% odd. And then you have Samsung Electronics, which actually came in from nowhere and carved its own position out, and it's growing rapidly in this place because it's pioneered a part of packaging called the panel level packaging. So you saw that in the previous slide, I had shown that the die is reconstituted on a reconstituted wafer, which is a 300 mm wafer. But Samsung's reconstituted that die on a panel, a display panel sort of a thing. So they are getting scale of packaging on it. So then ASE is an OSAT, or outsourced assembly test house, and they are the world's biggest, very innovative, and they again are a key player. Let me correct. It is not TSMC. It is ASE which took over SPIL. So if you take a look at it, this is what it is showing. The top 25 OSATs ASC, Amcor, PowerTech. PowerTech is actually the one of the first mover OSATs on the panel level packaging. And really, fan out packaging, fan out wafer level packaging, fan out panel level packaging, this is now almost mainstay with practically all the leading OSATs and foundries. This is what is coming in a big way. If you actually take a look at it, this is that simple semiconductor supply chain we talked of. This is another view on it. And take a look at how complex it's slowly getting evolving. You have fabless players, and then you have wafer foundries, and you have IDMs, and you have OSATs, and you have EMS. And now in the evolving era, there are people who are trying to eat each other's cakes. So really, what is happening is that Foxconn is trying to enter into the OSAT space, and OSATs are tying up with fabless, going and saying that we can actually do these things for your specific design for automotive. And Amcor will go and say it and try and take a share from the Amcom, from the automotive segment for packaging out there. And then there are foundries like TSMC who are trying to expand their fan-out capabilities and evolving certain unique features, which is why they are actually trapping some of the OSAT demand with themselves. And there are IDMs like Intel who are evolving with their heterogeneous integration platform or the chips platform with the US government support, and they are again having their own strategy to get into the space. So it is actually a huge market which is seeing fermentation. It's not fair to say it's cannibalizing because the market is expanding. Okay, and there's a huge opportunity which is getting created out of the innovations that are there. So quick messages out here. If you take the fan out wafer level packages, the advantage over a flip chip ball grid array, the fan out will be a smaller footprint, thinner package, substrate less package. So it will mean that you don't have the interposer cost, you don't have the other material costs, and because it has a lower thermal resistance and lesser material, it will be that much more efficient in its execution, processing execution. And wafer level chip scale packaging, so or a fan-in chip scale packaging, it will give you a better board reliability because you're not constrained on managing your solder ball grids to a very tight pitch, and therefore you won't have shorts coming up, and you won't get the integrity of the device getting destroyed by an improper packaging. So it's not no longer a wafer level CSP is no longer a favored packaging, strictly speaking, though you may still see some chips, but the world is moving over to the fan out packaging. And this is the key message. It's not just a smaller die size which can be accommodated out here. You don't have any more interposer. This interposer substrate, that you see in the flip chip CSP or the wire bond their designs, that is totally eliminated. This is actually a cost motivation to move towards it also, and the thickness is reducing, so that is a motivation. And this thickness also improves the thermal dissipation, so that is a motivation. So these are some of the things which are driving the shift to the fan-out wafer level package structure. And then the reality is, perhaps as you go ahead, if you take out the depreciation factor, okay, of the current material, current equipment usage, then you'll find that this is actually very, very practical. And as time goes by and depreciation just levels out, fan-out wafer level package will be actually getting that much more common and practical out there. So what is the cost analysis? If you are reconstituting on a 200 millimeter wafer versus you reconstitute on a 300 millimeter wafer versus you reconstitute on a bigger panel size carrier, you will find the cost structures can drop substantially, almost 1.5 to 2 times. And this means that the move towards panel level packaging is almost inevitable as you get into 20s. As I mentioned, Samsung and PTI are the two players who opened that front. but definitely the work will keep on going on. At this stage, I'm just presenting on the 300 wafer, but just you can also imagine if it was a panel, how it would be done. And basically the steps are simple. You have a tape lamination on which you place the chips, and you recreate the carrier with the with this laminated tape and the chips. And on this you put a mold and spin it over and cover all the chips with that mold. And then you take it through a furnace and let it get harder. You cure it and it becomes hard, and then you remove that carrier board, and you have the reconstituted wafer itself. This is the wafer, this molded wafer that is flipped over, and it is now the chips, the active area of the chip is facing up, and you planarize it, passivate it, and create wires in it to make the connections, and then put again appropriate patterning, etching, creating the landing pads on which the solder balls are going to come and sit. And effectively, you have created a package, and then you dice it. And after you have diced it, that is called singulation, you have got your packages. So this is, chip first face down design. And this is just to share that actually the wafer that you have created there, it's actually being subjected to the front end of front end of line for process. So you're going to create a micro bump. So you first passivate it and create a dielectric layer on that. You put some photoresist on it. You expose it, and then etch away the patterned area with the RIE or reaction ion etching, and then you put a metal bump on it, a solder bump on this, and then you remove the excess photoresist. So once you have removed it, you've got this anvil sort of a connection, and you saw it in this image that was there. Sorry, I will just try once more. So remember this image? This is actually, we are just reconstituting that. This is what has been done on that finished device. So this is a process, and you can repeat it for multi-chips. So this is a multi-chip system on chip, and you have a CMOS and a MEMS sensor, which is giving an analog signal to the processing chip, CMOS chip. And there is a memory chip, and there are passive chips out here. So this is a complete system on a chip. You put it on that carrier with the tape, and then you are actually putting an epoxy molding on it, and then you are reversing it, and you're creating a redistribution layer with all the interconnects etching on it, and you put the solder bumps on it, and you have effectively got your multi-chip system on chip. And this slide, the key messages, take a look at the interconnect counts that are being looked at. Info is integrated flip out chip, and this is the basic fan out thing. Different companies, different names, but basically the fan out chips, and how the cost structure is changing out from 45, from the cost structure is really coming down, cost per dry area, and that is the key driver for ATMP. Lower cost of the interconnection, get more interconnections up. That is where the fan out, that's where the OSATs and the industry is going. So if you actually take a look at the positioning of the OSATs, if you take a look at the positioning of the OSATs, this is what is happening. You have the top rung, which is the ASC and MCORs and PTIs of the world. So PTI is moved into the top rung actually. But this first batch is the fan out wafer level packaging leaders. And then PDI has led the wave on the fan out panel level packaging. And all this is how the OSATs are positioning themselves out. And then you have the foundries, and the foundries are also taking unique positions. TSMC is almost unbeatable on some of the things they're doing. They actually took away the iPhones Apple application processor engine chip, the main heart of an iPhone. That chip was with Samsung, and they actually are creating it now. And Samsung's reacting with its own panel level packaging technology, which they're going to take first to the Galaxy Watch. And I think others are slowly looking at getting into this area pretty aggressively. So where do we find this fan-out technology? So if you take a typical phone, take a look at it. This APE is actually a fan-out wafer level package. And if you really slice it open, you will see a main processor, and you'll see minimum two DRAM chips on it. Okay, and then you have all these other chips that have been pointed out, and green devices, they say, are what are going to be in the future, and gray that will likely remain with the chip scale packaging, and move to 3D IC or embedded die in future. So it's actually going to go out to the market. You see this moving more and more as you go ahead into different market opportunities in computing, networking, consumer. These will all flow in. You will see fan out there in communications pretty extensively, because in that level you will also be integrating antennas, and you will be trying to make sure that they are it's appropriately protected from the EMPs and radiation conditions. So a huge innovation is evolving in this area, and it's a market which is really growing. So if you take this a little more detail now, the same thing, and it's showing that the number of steps are increasing. And the only reason I put this up is that this is now slowly taking you into the manufacturing side of the picture. You have tools for all these things, and you actually in a real world, what will happen is, depending on what sort of chip you want to create, you will have an industrial engineer who will take the equipment inputs from the equipment manufacturer and lay down his factory. Just as I laid down the semiconductor factory, and showed you how that was created in my previous presentation, you will do the same thing in this. So the key conclusion is this. Going ahead, fan-out wafer level packaging is a mainstream packaging platform, and it will drive to lower line per space, lower pitch levels than ever before. You will find key applications in communications, power management, consumer, automotive, all moving on into fan-out packaging, because the OSATs will drive it, the end users will drive it, the fabless will drive it. Right now, it is pretty common for companies to be going to fabless and saying, "Hey, you've got this. Why don't you move to this new format? And this is the advantage you will get." And they then go and put pressure on their OSAT and say, "Hey, I want to move to this technology in my next roadmap execution." So there's this, the human innovation is phenomenal. It's not that fan-out packaging does not have its challenges, because just remember, you are putting silicon dies in a mold, and these will have different thermal coefficient of expansions, and this can create problems like warpage. Okay, it can have topographical challenges, because dies could be of different thicknesses, and then you need to manage that. And then your die itself, you have to have very precise positioning. And if there are die shifts, they can play with the overall, system functionality and reliability. So there are challenges, but these are all challenges that we are sure will keep on evolving and keep on getting addressed. So the key message: packaging, ATMP is not a simple area. It is evolving. It is tech intensive. All the things that you're talking of, it is very strongly design backed. It is very strongly backed by technologies. Literally, whatever you are seeing is actually created by advanced software like EDA, and simulated and tested, and then it is actually taken onto the physical world. It is driven by the increasing number of interconnects, a drive to lower the cost per interconnect, a drive to improve the functionalities. In future is even more exciting because now they're talking of the CHIPS program, which is a heterogeneous integration program, which is aiming at developing common IP usability. And the chiplets program by the DARPA US is going to be a very dominant program as we go ahead. Intel is a key partner to it. They have just been given the second phase of funding by the US government. So we should see more actions in it. Literally, the heterogeneous integration means that you have different parts of that new package having dies from different fabs at different nodes, and they are still getting integrated. But to make these integrations, yes, you'll have to define standards of how those integration interface points have to come up. And when you do it, the functionalities that would get created can be really very, very exciting and beyond. So I must now quickly take you through what Applied Materials does in this area. And you know that in my last session, I had covered the Medan Technology Center, which is a 40,000 square foot clean room. And then we have in Singapore, the Asia Product Development Center, which is operational for the last 8 years. We have a 17,000 square foot class 10 clean room. There are 40 odd tools out there. There are tools getting added out there, and there is a staff of over 70 R&D engineers out there. It's creating, it's got complete infrastructure for packaging, bump, TSV, fan-out, dicing, bonding, and it's been used for creating multiple new process flows, which can be integrated with customer sites as and when required. There have been products taken out on through silicon vias, fan-outs, bumps, and paper creations, and there are tools that have been adapted to these processes. So these are just some of the tools. I'll just flash you through it without getting into details of it, but the key messages are advanced packaging is seeing an evolution of the middle end of line process, taking some of the tools from the semiconductor front end processing into the back end processing. The process recipes are customized to individual end device for specific end sectors. They are designed with advanced EDA tools. It's not a guessware. You are given a process recipe from a technology provider, and that with that process technology, an industrial consultant will define the factory equipment by selecting appropriate tools as per output mix. In most cases, technology provider will give the factory equipment list to enable proven yield. A lot of this is not available on open markets as a technology sector. Industry specific standards are shipping out to evolve the heterogeneous integration, and that reality of the advanced packaging. So you're literally getting back to the future with what you are seeing. Part of my presentation, I just want to touch a little on the wide band carriers, wide band gap semiconductors, and this itself can be a full workshop later on, so I'll not get into details on it. But primarily, if you remember the school era and the science classes, there was a gentleman called Mendeleev who created a periodic table in which he laid all the known elements by their atomic number. And he found that after a certain number, if he actually repeated instead of in a single line in multiple rows, creating a periodic table, then people under a particular column, elements under a certain column, could have the same property. So he found that if we actually took hydrogen, and he put the next item as sodium and potassium, and these alkali metals or these alkalis were having same metal, and they were defining that starting column of the periodic table. And by his sheer vision, he was able to say that if there are certain items which are certain points in that periodic table which are empty because they are not having any element fitting into it, that must be because that element has not yet been discovered. Because when he created the periodic table, Mendeleev created that periodic table, there were only 62 items, 62 elements that were known. Today, there are 118 elements that have been discovered, of which 94 exist in nature. 24 have been proven in labs. Okay, they have been created in labs. They do not exist in nature. They are so unstable that they degrade out. So they have only been shown in labs. And what he has shown was that there were items like germanium and silicon, which could be positioned such that with a minimal doping, they could actually evolve in their electronic, in their electric, in their conducting properties. And then there were other materials which could be created by, for example, the gallium arsenide or gallium nitride. These are what are called the 3,5 compounds, and they are under the third column and the fifth column, and an alloy is created from them. And the beauty of these devices is that they actually are having a far higher energy, band gap energy. And band gap energy is the energy for taking that electron in the outermost shell of an element and ejecting it into a reaction. So if you take a look at it, what is happening here is that with the gallium nitride and with the wide band semiconductors, you are actually getting devices which could be having higher band gap energy. Therefore, to separate that electron from them would require a higher temperature or higher electric field. And that is why they become the basis for creating devices which could be used in much higher voltages and in much higher temperature conditions. So that is the positioning that you can roughly look at for wideband semiconductors. I have already got this here. So you can see band gap is the energy required to excite an electron from the valence band to the conduction band. And if the band gap is larger than a high, it will break down. So for the same breakdown voltage, wideband gap device will be smaller. And if it is smaller, it has a certain implication. For example, right now, the gallium nitride based devices are getting a breakthrough growth in fast chargers for mobiles. This is a development of the last few quarters that world is seeing the fast mobile chargers evolve using GaN devices. Okay, they are smaller, they have better performance and withstanding higher voltages, and it's reaching a stage that they may be more cost effective. So these are the reasons why wideband semiconductors will really have their position. Better thermal conductivity, higher thermal operating temperatures, smaller size, lower cost. Okay, so why do they just not replace silicon? Because silicon is cheaper. Silicon is much more stable as compared to gallium, for example, which is brittle and which is costlier and more difficult to process. So by and large, it is moved into niches, but it is growing in niches, and it is also going to be a multi-billion-dollar market and a subject for a separate workshop whenever that is planned. So the key message, it's going into power electronics, getting into communications, it's getting into chargers, into optoelectronics, into automotive, and again, a separate field in itself. So on that, I think I will end today's workshop, and I'm on time, 3 o'clock, 3:05, sorry, 7 minutes late. Any questions?
Dr. Ashwani, can I ask you a question? This is Pankaj Gulati.
Yes, Pankaj.
Hi. Uh, Basically, at what node do we need to change from the backside aluminum to the copper? At what node would you recommend that change? I mean, what is the industry trend from back aluminum to copper?
Can't say that. I'm not the expert on it, and it's actually crazy. I was reading a paper just before this, uh, which was actually talking of how copper itself had reached its limit, and those limits were getting extended as we went to, sub 10 nanometer.
All right, that's what meant. But I wanted to know that if you no idea, maybe I'll also hunt around the transition from the aluminum to copper. I mean, that's going to be very critical for any fab, because if you're getting a fab of 150 or a 180, I think that still uses aluminum. But moment you go around that, I'll check it out. Thank you. But thanks anyway. Thank you.
Dr. Agarwal, this is Ravi Bhatkal from McDermott Enthone. I just wanted to check with you, what is the current uh, infrastructure in India from a packaging standpoint? How much of die attach, or both back end of line and the actual packaging is being done today? And in your opinion, what would really need to be done in order to truly build up the infrastructure? Because logically, this is the next step in the Indian context, after board assembly. After PCBA, the next logical step upward in value is in packaging. What would you suggest would be the steps that are required to get there?
See, I believe value is created when you go closer to the customer.
Yeah.
And, if you go closer to the customer and decide and create a device with reference to that, you can really make money. But if you are going to create something where you don't control the customer, you could end up into a major capital exposure. So that is one reality. In India, our ATMP is in a very nascent stage at this point of time. I have seen some plants which are doing this assembly, and I think they are okay because they had a particular position historically. Uh, I can only say that going ahead, we have to be very careful on selecting what we are bringing into the assembly in the ATMP area, because it will be subject to a lot of very rapid forces, very turbulent forces on this.
So would you say that really you need to bring in an entire ecosystem, because you would need essentially, not just the packaging step, but everything in and around it, from
Ecosystem, yes, and ecosystem will come when you start with the customer. So what we always, what I have always maintained is, take certain markets that you want to target as a nation, try and develop your strategy with respect to that, capture that, and then you will be able to build up the ecosystem.
Sure. Yeah, thank you.
Ashmi, this is PVG Menon. One thing struck me as you were going through the packaging, the newer things, that there's a tremendous opportunity space for testing. Writing test software for testing the wafers and how they behave in the packaging. Any thoughts on that? Because already, as per the latest ISA report, the entire VLSI design, embedded software, PCB design space is already $25 billion and growing at about 17 to 20% CAGR. Do you see a similar opportunity for us here in this space as well?
I think testing will be an opportunity, but again, the pressures that are there are that a lot of the testing could start getting pulled back by the OSAT into their own turf. Because now the testing, as you saw, was taking place at the wafer level packaging itself. And therefore, that market could get impacted. Maybe not immediately, but over the decade, I think there would be a tremendous impact. The growth would taper off.
Okay, thanks.
So just for everybody's reference, I will upload this part of the presentation also on my website, www.india-inspires.com. Let me write it for you. I should have done it, but so you'll get it from there.
Thanks, Ashwani sir. That was a very wonderful and very enlightening lecture which you gave. So I request if anybody has any more questions, so we can ask Ashwani sir. So if not, then I'll request Marwa sir to say a word of thanks.
Okay. I think that was a very interesting session again. Thanks, Dr. Ashwini, once again, So I think we were benefited from your talk and a lot of information for us to imbibe. And we, in fact, thoroughly enjoyed it, and it was very informative. Thank you once again. Thank you, everyone, for participating.
My pleasure, sir.
Thank you.
Thank you.
Thanks a lot. Thanks.
Thank you, Ashwin. Thank you, Sudhir. Thank you.